Right. Thank you, everybody. Yeah, good morning or good afternoon. I don't know. It depends where you are, right? Yeah, okay. My topic today is SMAP-based soil moisture derivative data product over crop chasm for crop condition assessment. We recently released a soil moisture application. It's called a crop chasm. This is a web-based GIS application. It basically serves two major data products. One is the soil moisture data that's reserves 9-kilometer L4 data. That's a SMAP data product, and also we serves 1-kilometer soil moisture data product. That's it's aggregated based on the soil moisture SMAP data. And beyond that, we also serves that the modis-based vegetation indice data. And this application also provide a set of tools for analysis, to visualization, data manipulation, and also data dissemination. We also have a tools set that you can set region of interest for analysis, and we have ancillary data so that you can mask out the non-crop area so that you can focus on the crop area for analysis. Yeah, this is the interface of that crop chasm. User can get into it from the website address are listed on the top. So you click it, you can get into it. This is the online browser-based application. Yeah. With this, on this application, we have basically, as I said, we serve that the soil moisture data and the vegetation index data. We serve original SMAP 9-kilometer level 4 data, so which include that the topsoil and the root zone soil moisture. And we also serve that the 1-kilometer soil moisture data, which is derived from the SMAP data, and also the optical sensor modus and AVHR, And beyond that, we also did some processing and derived some derivative data product based from these two soil moisture data product. So we derived that daily, L4 data, daily, weekly L4 data, and also we developed the daily, weekly 1-kilometer data. Beyond that, we also derived that soil moisture anomaly data based on the 6-year historical data. And also we derived that the crop soil moisture condition map. This is the soil moisture condition map that is based on this soil moisture data and NAS weekly report soil moisture condition data. So yeah, this is the derivative data we are going to focus on. Beyond that, we also have the vegetation indice data, that's NDVI, VCI, and NDVI anomaly data. Okay, we have ancillary data served that they included the boundary data, county boundary, state boundary, and also that the crop mask and the water flow, that kind of boundary data. That's the standard from that census. Yeah. And here is that I'm going to showing that SMAP level 4, original level 4 data And this I just cutting the piece from that the hour state. You can see that for every 3 hours, it has output, so that you can, every day you have 8 output. So you will see that if you have a ring event develop, you will see that the moisture level changes, So this is and based on this original every 3 hour output, we basically aggregated this data by average them, so we can develop that daily average, soil moisture data, both top and root zone soil moisture data. Here is that example of the daily, average topsoil moisture data. You will see that the moisture level changes every day, but some place where you can see here that on the September 21st, you have that moisture, the rain events developed on the top right corner of Iowa. So this moisture level changes. So based on the daily, we develop the weekly average soil moisture data, so that you can compare between the years, the same months, what is the soil moisture level, you can look at that. So you will see that September 2016 is much wetter than the September 2015. The wind climate data is specially developed trying to gather that near field level assessment. So NASA got that Rajit Windrish led the development of that 1 kilometer high spatial resolution top soil moisture product. And based on that 1 kilometer data, so we basically do the same thing. We do have that weekly anomaly data and weekly average and the 3-day average, and also that weekly the soil moisture condition maps. These data product basically enable us to do a near field level assessment. So this is what it looks like 1 kilometer data. We'll see that this is the daily data. You will see these two are daily. Coverage is kind of better, but this one is coverage is very small. So overall, you will see that the 3-day, sometimes you will still have some gap here, but sometimes you can have a full coverage. So weekly, basically, put all the daily data together, to take average. So that's we develop the weekly. So weekly, we basically have a full coverage of that called US. And when we look at that, the granularity, when you zoom in, you will see that the weekly data is much, the 1 kilometer data is much better than the 9 kilometer. Yeah, as we will see this. And the derivative data, that the anomaly data, it's very simple. We just compare the current the soil moisture level with the historical average. So, so this is the results what we look at. We can see from the average, from the anomaly. You will see that. So, and another major derivative data is that this crop soil moisture condition map. This is the data we cannot directly from that moisture level, soil moisture map alone. From the barometric data, that the information does not really tell us, which level is, is that good enough for this crop, or that's short for the crop, So this is, we definitely need extra information. The extra information is coming from NAS weekly survey report. So every week we report that soil moisture level for that at the state level. And we basically have 4 categories. So it's so much of the soil moisture level to the crop. So one is that the very short, the other is that the short, the other moisture level is adequate, or this you have the moisture level is too much. You have too much water, so it's surplus. So we have 4 level, and the survey will calculate that, will report that the percentage of that the whole state that's in which category. So we have, like for example, here we have 1% is very short, 5% is short, 86% crop land that's adequate, 8% is surplus. It's an example, But from this report, and also from the SMAP volumetric soil moisture data, then we can develop a soil moisture condition map. The key here is that we found that there is a one-to-one map relationship between that the reported the category percentage and the volumetric data, historical the histogram, cumulative histogram. So you will see that there is a one-to-one match. So you based on this mapping relationship, then you can find the threshold to get a cutoff that the level of that the volumetric measure that corresponds to that every category of the NAS report. So this is the basically we based on this percentage category coverage, we map to that the cumulative histogram, and then we from that curve we can find that what is a volumetric measurement. That is a cutoff spots, so that based on that you can see, okay, below this will be very sharp, and below this XS level, that's the sharp, and so on. This is how we develop that. And this is
quick question on the last slide. Where did you come up with your percentile thresholds for very short, etc.?
This is from the NAS report. We report that we do have a survey every week. So that's how we fix that. Fix this map. We can translate this into that the condition map. Yeah, here is that the condition map, and but it applied a crop mask, so that you will see the gray area that's non-crop area, all the other color that's the crop area. You will see that different crop area has a different soil moisture condition level. Yeah. So here is that case study based on this data, and we can see that how we can analysis that the 2021 Western drought. Here I look at the study area where I look at is that the Columbia Basin in that Washington State, Grant County, and this is basically the study area. We see that this is a bunch of crop here. And from that, the soil moisture anomaly, we will see that this is the dry 5th week, 12th week, and before until that August 15th week, you know. You will see here the anomaly is that the moisture level is not that bad on the first first 2 weeks of the July, you know, and especially this week, July 12 to 18, the moisture level is okay compared to the historic. Times drier, and the other 2 weeks it looks like is not that bad, you know, the moisture level. But the actual condition, the measure reported by NAS and the condition map from our derived condition map, soil moisture condition map, we'll see here on the first of the dry that week, we have one portion of the area that's extra. So this area has a lot of, this is basically is an irrigation area. So we can tell this area has a lot of irrigation activity. And this week, and no irrigation, and no irrigation, you know, the moisture level, the condition is still, it's kind of short, not a very short level. So then at this level, week, August 1st week, we'll see many farmers, they did irrigation, you know, or rain event happen. And the next week is the same thing. So, but I'm not sure it's raining or they systematically irrigate, but it definitely has a moisture level increase. From this, we can see that what the response on that vegetation, you know. The first week we'll see that it's very bad, you know. It's the condition wise, it's a stress, lots of areas of stress here, especially you see that. And this area looks like it's kind of better, but if we go back, compare this, yeah, that's probably, you know, take some, the moisture level actually translating into that vegetation condition, you know, it becomes less stress compared to this one. So this one is the same thing, you know, but this week you can look at the July 26th week, so then it become stress again, you know, compared to the previous week, you know. But if you go back, so it's not no irrigation or rain event happen here. But if you look at the condition wise, it is not that bad, you know, compared to the history. Okay. So the next week, okay.
You're about 18 minutes in.
Okay. And not this one. Yeah, then the August 2nd, that week, the stress level is less, and what's going on? And this week, the August 9th, the vegetation is even less stress. So you look at this, that the moisture level, you will see these 2 weeks, you know, is the last 2 weeks here we see that's a lot of that moisture level there. So either irrigated or rain events. That helps the vegetation stress a lot. But we notice that there is a delay, you know. Yeah, so that's this is that the case study about that from the 1 kilometer data. This slide is showing you that the corresponding area, but this is the 9 kilometer data. But the 9 kilometer data looks like we'll see here is that it does not capture that the irrigation activity or this local area, raining or something like that. So this is really definitely is that the resolution has a bigger issue here. So for that, the field level response, this is not good, you know. Okay, so this is the how that the our derivative data can help that assessment of that crop condition, you know. Yeah, this is I'm trying to just go through that what the application being used in as. So this is the condition map is being used, and the soil moisture data has been used. It's become part of the crop weather report, you know, and also it being used to assess that the flood beyond that drought we just talked about. Okay, that's all what I have. Yeah. Any question?
Thank you, Zhengwei. There are a few questions in the chat. I'll read the first couple, okay, and then you can follow up with the remaining as we move on. But I already asked Ron Leeper's question about how do you come up with the thresholds. Kent Sutcliffe is asking, is the 100% surplus threshold in theory at least supposed to correlate with field capacity? Is that field capacity or is it flooding or ponding in the fields? These are things set by the farmers. Is that right from your surveys?
Yes, this survey basically is the 1%, how this 1% count. It is 1% is sort of you know, very tricky number. You know, that means not significant. But from that state, you have usually lots of county there. So basically every county you have a couple sample. This number correct from the farmer and the extension staff and also NES staff, you know. So they have, this is a volunteer-based survey, not a strict, you know, system designed survey. It's a different, you know. So it's, yeah, you could, you say 1%, could it be like 3% or 5%?
100%. What's 100% equal?
100%, it means every place that's you know, the very drought. If you say it's 1% very drought, very short, every place very short. If you say 90%, that's 90% of the cropland, that's very short. It's only talked about cropland, not the non-crop area.
Okay. Okay. Yeah. Carolyn's posting some information in the chat as well for folks, but we're going to move on. I'll direct you to the chat to look at Elisa and Yulong, and then Dan have some questions that you can respond to. So thank you very much.
You're welcome.
We're going to move on to a presentation. I can make my screen share. Our next presenter is Saab Kim at JPL, and he will be presenting on field scale soil moisture estimation. And he is in the chat, I believe, able to answer questions as we go along.
Hello, today I'm going to talk about field scale surface soil moisture mapping from airborne and spaceborne sensors. hoping to replace the background optical image with soil moisture maps if possible. I'm Seung-Bum Kim from NASA Jet Propulsion Lab. Co-authors are Tianhao Liao from the same institution and Mike Koch. Some of the results are made in collaboration with Alisa Coffin, David Bosch at USDA, and Argentinian colleague. This work is supported mainly by NASA flight project and research programs, also US Interagency Satellite Needs Working Group funding. To choose which sensor is best for us to meet our goal, I list some of the details of available sensors. The airborne has the spatial resolution of 6 meter. Spaceborne spectrometer or radiometer like SMAP has the resolution of 1 kilometer to about 25 kilometer. Future spaceborne radar offers about 100 meter. The weak point of airborne is the revisit time. Because it's on demand, revisit is irregular. On the other hand, spectrometer and radiometer offer 3 days, radar 6 days. Sensing depth that's determined by the operating frequency ranges from 3 centimeter to 20 centimeter for wet soil. And for dry soil, we multiply by a factor of 4, so we can reach the root zone. These optical images show what resolution we really need. On the left is Iowa farms, and we can see very small scale fields. For identifying this, we need about 100 meter resolution. On the right is Montana, where water supply comes from the stream or the ground, and also with the hills, the shape of the fields are very irregular and the sizes are very small. Clearly, we need something like 100 meter. These are the same contrast of what resolution we need, but in terms of the soil moisture maps available. On the left is 1 kilometer resolution soil moisture map over Canada from SMAP product. Circles are 36 kilometer footprint, each pixel is 1 kilometer. We cannot quite see which field is which, but on the right is 18 meter resolution from airborne sensing over Tifton, Georgia. This is 1 kilometer, and we can clearly identify all the field boundaries. So definitely we need about 18 meter or 100 meter to clearly resolve the fields in soil moisture maps. This one, just one page, summarizes the algorithm. Like many inversion methods, we establish for the model of the sensor and then invert it. So these cubes are population of the Ford model calculations in the polarizations of HH, HV, VV, and then we invert it. On the next slides are the examples of the field scale soil moisture maps. First is the agricultural case of top 5 centimeter. The domain is 80 kilometer by 20 kilometer in Canadian prairies. The rectangles show the airborne swaths. The dots are the in situ sites. Inset is the precipitation. This series of maps are the soil moisture of 4 selected days. The first one is day 171, which is here, after rain, and the big rain event. Everywhere is wet according to this color scale. And dry down continues after this event. So day 179 here, day 190 shows the continued drying. But then there was a big rain event 195. So especially in the central area, we saw the soil moisture increased from here to there. So the temporal variations of this retrieval map seems realistic. Next is the quantitative evaluation of the retrieval. X-axis is in situ, Y is the retrieval. For 4 major crops, pasture, soybean, wheat, and corn. And especially soybean and corn, the crops started from the seed to the full growth. The RMSE values range from 0.04 to 0.06. Correlations are high. So with these results, even when the crops change from seed to the full, we are able to achieve these results, and with these results, we'll be able to distinguish the soil moisture levels of 4 or 5 states. Next is the surface soil moisture maps over landslide applications on hills or topography at 6-meter scale. Objective is to see whether high-resolution soil moisture maps are helpful for understanding and predicting landslides. The target is the California landslide regions. And in California, there are a lot of landslides. And if you remember, Oprah Winfrey's house was mudslided 2 years ago and was featured in the national news. So this is the domain of 50-meter and 300-meter. Over 3 years, our retrievers were able to showing all the details of the spatial variation of soil moisture and temporally wet in winter, dry in summer, and showing the progression temporal correctly. So most of the landslides occur in winter. At this red dot, there was a sensor, and we validated the retrieval results. The outcome shows that the retrieval was good to 0.05 cubic over cubic. So with this result, we are hoping to advance the landslide science and applications. Next is the soil moisture maps for forest science at 100-meter scale. The objective is that, as shown by the neon and SMAP comparison yesterday, with radiometer, there's a difficulty in retrieval because of the strong attenuation. In comparison, radar may have an edge, which we want to see. So we chose the aspen forest in Canada over 3 weeks period, and the forest looks pretty thick. The retrievals are shown by the scatter diagrams in the below. X is in situ, Y is retrieval. The RMSE is 0.03, 0.04, correlation is high. So this result suggests that even in forest, radar has some skill to tell us the soil moisture information correctly. Another case is that this retrieval algorithm seems to be able to cope with the changes occurring with harvest practice. So when there's a harvest, ground roughness increases because of the tractor and manual operations. And also vegetation amount decreases because the crops are removed. And our retrievals correctly show these changes, and we used the SMAP radar data over Argentinian pampas. So x-axis is the 3-month SMAP radar period in 2015. The top is the radar observation. Up to this point, most of the changes are due to the soil moisture and some row effect. But at this stage, there is a big drop in radar reading, which is associated with the removal of the vegetation. And that is shown by the retrieval of the vegetation amount in green. It's a big drop here. Corresponding changes in roughness shows in blue an increase, which indicates the tractor operations. So I'll make a summary. In this talk, for applications of agriculture and landslide over topography and forestry, we demonstrate that surface soil moisture maps are possible at 0.06 cubic over cubic RMSE accuracy, and that's the surface from top to about 5 centimeter. With airborne radar at longer operating frequency, we expect that the sensing depth goes down to 20 centimeter or even deeper when it's dry, which approaches the root zone. The matching spatial resolutions are 6 to 18 meter with airborne and 60 to 100 meter with satellites. The corresponding temporal repeat of observation is 6 days with the future NASA ISRO synthetic aperture radar due for launch in summer 2023. Finally, we are exploring collaborations for ground validations and applications. Thank you.
Thank you, Saab. And do we have any questions for Saab? I see none in the chat. If I don't, I'm going to move on for time. So Saab will be in if something strikes you. Just post it in the chat, he'll respond. So we'll move on to the next presentation from Lisa Wernicke. Sorry if I butchered your name. And you are in the chat as well, so another opportunity to engage with the speaker. Sorry about that. Was no one hearing that?
No, we were not, and I apologize.
I will. I just need to reshare. So hold on a second. I can hear it perfectly fine in my ears.
Yeah, we couldn't see it either.
Yeah. I was a peculiarity of how Zoom interprets the application. So let me get it to go.
Hi, I'm Liza Wernicke. I'm a graduate student at CU Boulder, and I'm working with Clara Chu and Eric Small to merge SMAP and Cygnus observations to create a downscaled soil moisture product. The motivation behind this project stems from the fact that SMAP's original plan included a downscaled soil moisture product using SMAP radar. However, the SMAP radar became non-operational shortly after launch, and there have since been different attempts to downscale SMAP using other radar data. On the left side of this figure, we can see SMAP 36-kilometer brightness temperature data near Yuma, Arizona, and the same geographical area is shown in the Google Earth image on the right. Here, the irrigated croplands with higher soil moisture content should have a lower brightness temperature than the surrounding desert. But at this coarse 36-kilometer scale, these landscape features aren't discernible. If we downscale SMAP to create a higher resolution product, then more landscape features should be visible in the data. So our goal is to combine coarse scale SMAP brightness temperatures and fine scale Cygnus reflectivities to develop a downscaled soil moisture product, hopefully a 3-kilometer product. Before discussing algorithm development, I'd like to briefly introduce the NASA Cygnus mission. Cygnus stands for Cyclone Global Navigation Satellite System, and there are 8 Cygnus observatories in orbit, each with L-band bistatic radar receivers. L-band is the same microwave range that SMAP uses and is effective at detecting soil moisture. As depicted in this figure, a bistatic radar receiver, or a GNSSR receiver, in this case Cygnus, detects signals that reflect off the Earth's surface after being emitted by different satellites, in this case GPS satellites. Each of the 8 Cygnus observatories can measure 4 GPS signals at a time, meaning that there are many Cygnus retrievals every day. All the Cygnus observatories follow low inclination, low Earth orbits, creating a latitudinal range of plus or minus 38 degrees. This tropical latitudinal range is by design, as the original mission objective is to observe wind speeds in tropical storms. The minimum spatial footprint of Cygnus over land is approximately 3.5 by 0.5 kilometers, which is fairly high spatial resolution. This figure shows all Cygnus observations on August 5th, 2020. Even though Cygnus observations have good daily low latitudinal coverage at a coarse scale, at a 3-kilometer spatial scale, the global repeat period is about 8 days at higher latitudes and closer to 14 days near the equator. Cygnus data are originally recorded as delayed Doppler maps, an example of which can be seen here. In order to use the Cygnus data, we locate the peak power signal from each DDM, convert the signal to decibels, and use the bistatic radar equation to calculate an approximate surface reflectivity. Now we can discuss our brightness temperature algorithm, which is adapted from the original SNAP radiometer radar downscaling algorithm, altered to work with Cygnus data. Next, I will step through each variable in the algorithm. The first term on the right-hand side is the SNAP vertically polarized brightness temperature at the 36-kilometer scale, where C is for coarse scale. For each term, I've included an example map of India with values averaged over the year 2020. So this map is showing the average SNAP 36-kilometer brightness temperatures for 2020. The second term on the right-hand side includes beta, which I'll talk about in the next slide, multiplied by the difference in coarse and intermediate scale Cygnus reflectivity values. The intermediate scale map in the middle shows average Cygnus reflectivity values at the 3-kilometer scale for 2020, and the coarse scale map on the right shows average Cygnus reflectivity values at the 36-kilometer scale for 2020. Beta, or slope, is the linear relationship between SNAP brightness temperature and Cygnus reflectivity. For the example I'm showing today, we are using the median slope for India, which is negative 2.763 Kelvin per decibel. Our goal is to use spatially varying slopes, and we did calculate spatially varying slopes over India at the 36-kilometer scale in order to determine the median value. However, we chose to use a single median value for this example because some of the calculated slopes are very close to 0, either due to minimal changes in reflectivity or minimal changes in brightness temperature over the area. Looking at the algorithm, a slope value of 0 is obviously a problem, and we are still working on how to deal with this issue. So after adding the coarse scale brightness temperature to the slope multiplied by the difference in Cygnus reflectivity values, we calculate the vertically polarized brightness temperature at the 3-kilometer scale, where M is for intermediate scale. The map on the left shows the calculated 3-kilometer brightness temperature values, again averaged for 2020. Zooming in, taking a closer look at central India, we can clearly see more geographical features in the 3-kilometer brightness temperature map than the 36-kilometer map. Here's one final example, looking at a much smaller geographical area near Yuma, Arizona. This is the same Google Earth map that I showed on the first slide, but here the map on the left is displaying Cygnus reflectivity values at the 3-kilometer scale. The color bar shows that dark blue is the highest reflectivity in decibels, where higher reflectivity correlates to higher moisture content. We can clearly see the Salton Sea and the Colorado River have high reflectivity values on this map. More importantly, the irrigated croplands with higher soil moisture than the surrounding desert also have higher reflectivity values. Now, comparing the 3-kilometer Cygnus reflectivity map on the left with the calculated 3-kilometer brightness temperature map in the middle and the SNAP 36-kilometer brightness temperature map on the right, we can see much of the same detail in the calculated 3-kilometer brightness temperature data as in the 3-kilometer Cygnus reflectivity data. Specifically, the Salton Sea, Colorado River, and irrigated croplands are all discernible in the calculated 3-kilometer brightness temperature map, but not in the SNAP 36-kilometer data. While we're looking at this figure, I want to bring your attention to an issue we will need to resolve while finalizing our algorithm. I've outlined one 36-kilometer SMAP grid cell in black on the 3-kilometer brightness temperature map, but you can probably see more of the SMAP grids as there is a distinct boundary artifact where the brightness temperature values abruptly change at the SMAP grid boundaries. As with our India example, we used a single slope value to calculate these 3-kilometer brightness temperatures, and we hope that incorporating spatially varying slopes will reduce the boundary artifact. But if it remains, we will need to consider other options in order to reduce the boundary artifact in the final product. We're still in the early stages of developing our brightness temperature algorithm and have many items to consider and complications to resolve. Among these, 2 are particularly noteworthy. Firstly, we are still considering how the slope or the linear relationship between brightness temperature and cygnus reflectivity should vary both spatially and temporally. We may calculate spatially varying slopes at the 36-kilometer scale or at the 3-kilometer scale. We also want to explore if there is a relationship between slope and land cover class. Additionally, we will explore the possibility of temporal variations in slope, especially seasonal variations due to changes in vegetation. So we may calculate spatially and seasonally varying slopes. Secondly, sparse daily cygnus observations lead to sparse daily 3-kilometer maps, as can be seen in this figure, which shows all the cygnus observations recorded on August 7th, 2020, over a small region in India. The red box in the figure is a 36-kilometer SMAP grid cell, and we can see that there are only about 15 cygnus observations within this SMAP grid cell on this day, which means that at a 3-kilometer scale, there would be a lot of gaps in the data. So we are trying to determine how to adjust the temporal and spatial resolution of the final product in order to reduce these gaps and improve usability. We have considered averaging all cygnus observations over the 2 to 3 days between SNAP observations and creating a product with the same temporal resolution as SMAP. We've also considered adjusting the spatial resolution of the final product, maybe to 4 or 5 kilometers instead of 3 kilometers, in order to reduce data gaps. Finally, the title of this presentation mentions a soil moisture product, but so far I've only discussed the brightness temperature algorithm. After the brightness temperature algorithm is finalized, sometime in the future, we will explore which SNAP algorithm and which ancillary data sets will optimize the accuracy of the final soil moisture product. Thank you for your time. I look forward to your questions and comments.
Thank you. And do we have any questions in the chat? It is a little hard to navigate right now through the other comments going out there. I don't know if I see any specifically for you, Lisa. I would ask, and let me unshare here. So what's the prognosis going forward? Is there any ability to get, so the data set, you're dealing with Cygnus, so C is cyclone limited by latitude, very optimized for Africa, is almost completely captured in that. What are the possibilities of having the resources to have this covered across the entire CONUS at least?
Well, I think we would need a new satellite mission. So Cygnus was specifically for cyclone, but part of the reason that we're doing this research, trying to create this product, is to show that if it can create a good soil moisture product, then we could, the Cygnus mission are very small satellites, and so it was a low expense mission. And so if we can demonstrate that it's an effective product, maybe we could send up more satellites that would have better global coverage.
Okay, because I think there's other data sources out there, or will come online eventually, that, because this isn't the primary purpose of Cygnus, so it's measuring other things. So these other rationales, these other platforms monitoring other similar things, and who knows how far north cyclones will go in the future, so there's potential future application at other latitudes. is my statement, I guess, not a question.
Mike, Spire has 2 satellites in polar orbits that are currently doing the same type of measurements as Cygnus, and will launch future satellites as well. So there will be plenty of GNSS-R satellites in the future to do this type of work.
Okay. And you have a poster discussing that today as well?
Yep, in just a few minutes.
Yep.
Awesome.
Okay.
Thank you.
And so the question, using single beta value for India is sufficient given its length and its breadth. Is using single beta value for India sufficient given its length and breadth and variation of social or soil orders and vegetation types? I cannot read today.
No, so that was just for the example. We're hoping to have spatially varying slopes for the whole product globally, at least in the latitudinal range that Cygnus covers. And so we did calculate the spatially varying slopes for India, but some of them are close to 0. So we need to look at how to adapt the slopes that are close to 0 so that they are not close to 0, so the algorithm works. So we've considered looking at if there's a relationship between slope and land cover class, and then if there are some slopes that are close to 0, but nearby there are some slopes that are non-zero that are the same land cover class, then we could just apply those slopes instead. Would be one way to solve that problem. But no, definitely we do intend to have spatially varying slopes.
Okay. There's another question or two in the chat. I'll let you go investigate them. So right now we're at 12:55. We have a couple of, and thank you, Liza. Right now we have 2 options. We would normally be taking a 5-minute break and returning for poster sessions. Is there, and we can do this by a show of hands, interest in doing another 5-minute breakout, just to have other people meet and mix and mingle. You can, if you, in your browser, if you see the more button, the reactions button, there's a place there for thumbs up. If you click on the reactions, just give me an idea of, are people interested in having a 5-minute breakout or just a 5-minute break and return on for poster sessions? I'm seeing a few thumbs up, so that's what we're getting. And we'll delay the poster by 5 minutes. So I'm going to create 10 random breakout rooms, and you all have 5 minutes to go in, have a little chat, and meet some people you might have met before. And then we will reconvene in a big room at 1:05 p.m. Eastern Daylight to have a discussion about poster sessions and where to go and how to get there. Okay. Have fun meeting new people.